think we can just get started. Good morning, everybody. I hope you're interested in video for Linux. I know there's a couple of people who came in the room and then decided that it wasn't for them. Hello. I'm going to start this presentation by asking you if it would be useful to have a really quick introduction about the key video for Linux concept, or just a quick reminder. Would anyone find that useful? That's good, because I was planning to do it. Thank you. All right. So video for Linux. I assume you're familiar with either video or Linux, and preferably both. So I'll just go really quickly over the key concepts. No, not going into details here. I've been told during the last talk I gave, that was on the display side, that I nearly killed half of the audience by showing way too much code on the slides. So today there's not going to be any code. Instead of that, you will have, well, quite a few pictures with cute penguins. I hope that's fine with you. So video for Linux, at the core of it, is an API between user space and kernel space, where through a video node, a user space application can interact with a device in kernel space. So what can you do through that? There's a couple of operations, and I've split them in 3 configuration operations, and then a couple of video streaming operations. So again, without going into details, the first one is configuration of formats. When I'm talking about formats here, I'm talking about the pixel format as captured in memory in a buffer. I'm talking about the video resolution. I'm talking about cropping. I'm talking about scaling. So it's really covering all the concepts without needing to differentiate between them that relate to the size and format of the image. The second concept, by the way, I've used different pictures that you will see again and again in all the slides. So try to remember them, because I decided not to put too much text on the slides. So this means everything that's related to the format. And you see an image being scaled down to a smaller size. This picture is everything related to controls. So a control in video for Linux is really a knob that you can turn, something that you can tune to change the parameters of the video processing, basically. And so this image shows 2 parts of a single picture, one with full color and one in grayscale. So you could imagine controls that can handle contrast, brightness, hue, saturation, any kind of processing like that. So we have currently 175 standard controls in video for Linux and many device-specific and driver-specific controls. So there's quite a few of them. The third operation is everything that's related to buffers. So once you have configured your device and your formats and possibly set controls, you need to allocate buffers in which video and frames will be captured. So video for Linux has extensive support for buffer management. It handles at the core a queue of buffers with 3 currently different memory models where you can allocate and handle memory that is DMA contiguous, that uses scatter-gather or uses vmalloc. Drivers can actually extend that and create new memory models. We have support for DMA buff, so there's a lot that deals with memory management. Again, that picture shows 4 different buffers with 1 image in each. So that's the 3 configuration parts. When you want to use your device, you configure your formats, you set your controls, and then you locate your buffers. Then it's time to start video streaming. Hopefully this picture is quite clear, and the last one as well. You start your video stream, and then it's really about passing buffers between kernel space and user space. And that's what this picture represents. You have a set of buffers, and they cycle between user space and kernel space. So you give buffers to the kernel driver will queue that to the hardware will fill the buffers with images, and then you get them back in user space, you process the buffer in user space, pass it back to the kernel, and just loop like that. And then when you're done, you stop the video stream. So that's really really quick introduction about the video for Linux concept. I mentioned that we have a device node, for the interface between user space and kernel space. Well, in many cases, you actually have more than one. So it's quite typical on consumer devices that you find in the PC market to have, for instance, two video nodes. One that can be used to capture uncompressed images, one that can be used to capture compressed MPEG, for instance, images. Then, if you have multiple video nodes, well, you basically use them the same way as a single video node. That means that you configure formats, you allocate your buffers, you set controls, you start streaming, you dequeue the buffers, and you can do that independently for the two video streams. So you got the uncompressed stream at the top, the compressed stream at the bottom. You don't actually have to set controls if that's not needed by your application. You don't actually maybe need to configure scaling if that's either not available for one of your video streams or if you don't need that. So it's quite flexible in what you have to do, but the basic concept is the same. When it comes to the kernel space now, for quite some time, we've realized that having a single driver in kernel space that handles your whole video device is not a model that can scale. Because usually your video device, the hardware, will be made of multiple hardware pieces that are independent from each other, in the sense that they usually come from multiple vendors. You could have, again, in an embedded device, video capture interface in your SoC. You could have on a PC device, you could have a PCI bridge on a PCI capture card. And you can have other devices there. You could have a camera sensor. You could have an HDMI decoder or an analog decoder that will feed data, digital data into your bridge. And because those chips can be mixed and matched in different devices, we have a framework in the kernel that you can use to create separate drivers for the separate chips and just use them and combine them together. So that's what we call in video for Linux sub-devices. So a sub-device is a part of your hardware device that is modeled as a separate entity in the kernel space, and the sub-devices can interact together through an abstract API that is not device-dependent. So that's very much hidden in kernel space. How does that work? Well, when you have a user space call, talking about set format as an example here, it's going to go through a video node to your bridge driver, and then the bridge driver will decide what to do with that. So it will try to set the format on the decoder driver, for instance, to configure a scaler, to scale down or scale up. The decoder, sub-device, the driver, might or might not accept that. Maybe your decoder doesn't have a hardware scaler, in which case it rejects the call and says, I can't do that. If it can, that's fine. If it cannot, maybe you have a scaler on the SoC side, and then your bridge driver can configure that. So it's really communication between separate drivers in kernel space through an API between the two. I'm talking about formats here, but it's pretty much the same concept for everything. When you want to set controls, when you want to start and stop video streaming, obviously if your application wants to start a video stream, then you need to start all the pieces, all the hardware pieces that, that will carry the video stream. So that's really the same concept. Then we realized that it's actually not enough when you have more complex devices, and especially in the embedded world, when you can have quite a lot of sub-devices. Even inside your SoC, your camera interface could be split in different processing blocks, and maybe multiple of them will have similar features. You could have an external camera sensor that can do scaling. You could have a scaler inside your SoC. And the kernel doesn't have enough information just from what it gets through the video nodes to decide exactly how to configure the device. Again, if you have multiple scalers, we have an API in Video for Linux to configure scaling, but that API doesn't tell where to scale. And you might decide to scale down on the sensor with a lower quality scaling if you're really interested in fast video capture, for instance, while for still image capture, you want the best quality scaler that's going to be on the SoC. And so we've extended the Video for Linux API with a different kind of video node, so a different API to user space. It's still part of Video for Linux. And that exposes the sub-devices to user space. So instead of having only communication on the kernel side between your bridge and your sub-devices, then user space can directly interact with the subdevices and actually configure the formats and configure the controls directly there. So you can imagine a video pipeline made of multiple subdevices, and user space will be responsible in that case to configure formats on every point on the pipeline. Give a bit more information about that later. So from a configuration point of view, when using subdevices that expose a user space API, it's the same concept. You're going to configure formats, set the controls, and do that once for every subdevice in your video pipeline. So no rocket science there. You just need to ensure that the configuration you set across the whole pipeline is consistent. Usually, kernel will verify that and tell you if it isn't, but it's user space responsibility to make it consistent if you want to make it working. So that was video for Linux. Any question? Okay, if there's something that's unclear in the presentation, feel free to interrupt me. If it happens too often, I might push the questions back to the end of the talk. But for now, that's fine. So the second piece I want to introduce is the media controller. Media controller is, again, a separate API. The need to have that API came from the Nokia days when we were working on camera support for the Nokia N900 and N9. And we found out that having subdevices just in the kernel wasn't enough, that we needed to expose the subdevice to user space with the user space API I just talked about, but then we also needed to expose the topology of the device to user space. So instead of just having video nodes and having user space either guessing what's inside the kernel, what the different pieces are, or user space having to hard code all that assumption for every possible device, and so being less portable across devices, we've created an API that can be used to model the video device, the hardware device, and that API works in conjunction with the Video for Linux and the Video for Linux subdev user space API. So once again, when you see this symbol, that means a video node or device node between user space and kernel space. If the bottom part is blue, that's a Video for Linux device. If it's red, that's a subdev. And if it's yellow, that's a media controller device. So I'm going to reuse that a bit later in the talk. So we now have a media driver that gathers all the different pieces, the bridge driver, the multiple subdevs, and that can expose the topology of the device to user space. So how does it do that? Well, it models the device in an abstract way using a concept called entity. So an entity is basically a building block. It's something that can process data. That's pretty much it. Entities can have paths. They're numbered, so you can see an entity here with 3 paths, 2 inputs or sync paths, and 1 output or source pad. They can have any number of paths, it's variable. And then the entities are linked together, you can see the arrows here, from pad to pad. And so the idea is that this models a graph of the video pipelines. So in this case, well, there's something that's out of the picture here. You have 2 video streams coming in this entity. It could be, for instance, a switch that selects which video stream to take, or could be maybe a composer that takes a 2 video stream and composes them with alpha blending. And then it feeds data to another entity here. You have a 3rd one and a 4th one. And links can be active, in which case the arrow is plain, or inactive, in which case it's dotted. So the media controller can model the device, expose the topology to user space, so user space can know what's inside, and can also be used by user space to set up the links and activate or deactivate them. So that's really the core of it. It can be used to model, well, pretty simple devices. So that's an example of something that's been working on in Xilinx FPGA. It's pretty simple. We have an HDMI receiver at the top that's external to the FPGA. We have a test pattern generator here. We have a scaler and then a video node to capture data to memory. So it models the DMA engine. It can be more complex than that. I mentioned Nokia phones. That's the camera interface and video processing that you find in the OMAP 3. So you have all the green blocks are different subdevices. All the yellow ones are different video nodes or DMA engines. And it can even be more complex than that. I've recently had to work with a Renesas chip that has a memory-to-memory video processing engine with 5 inputs and 4 outputs, and the graph looks like that. So there's no limit to the complexity you can have. The reason it looks so complex is actually that every output of an entity can be connected to any input of any other entity. So instead of modeling all possible links like that, it would probably be a good idea to model a big switch matrix, something like that in the middle. But again, you can have really simple complex devices. Yes?
Does this functionality overlap with what GStreamer offers? Or?
Yes and no. So it's a similar concept. But what GStreamer does is indeed, it models elements that are connected in a pipeline, and it will push buffers and data through the pipeline. But GStreamer more or less assumes, that's not always the case now, but at least it was designed to assume that you have memory buffers between the elements, and that it can actually schedule the elements and push the buffers around. While this really models the hardware. So all the links you see there, they're really hardware links between entities. And we do have GStreamer elements that use the media controller API to configure a video pipeline inside a hardware device with all the hardware links, and then expose that as a single GStreamer element where you can push buffers in and get buffers out at the end parts of the pipeline, so at the video nodes at the top here and at the bottom.
Will you be talking about how you handle buffers?
Not much, but if you have a specific question about that, maybe we can talk about that later. But
yes.
Okay. So there's a few problems there. And that's why the idea of the request API that I'm going to talk about came to Hans first and to me. So the problems we have is, well, one of them is how can you synchronize controls to video buffers? So let's assume that you're capturing a stream of images. You have 30 frames, 60 frames per second. And you want for every frame to apply capture parameters. So you can use the setControl API that we have in Video for Linux to set a control. But that's not synchronized with the video buffers. So we have no solution for that today in Video for Linux. You can, well, there's a best effort approach. Well, if you apply your control from user space right after the beginning of a video frame capture, then it's going to be applied to the hardware at the end. And well, if the timing is right, you're not going to miss the VSync between the frames, and it should be OK, but there's no guarantee. And that's not good. We have requirements coming from Android, for instance, but also other user space APIs, where user space really wants to be able to apply a bunch of parameters for every frame that it captures. So that's what I'm trying to model here. One example use case of that is exposure bracketing, where you want to capture different images with different exposures and blend all that to have some kind of HDR processing. You definitely don't want to miss setting a control. Otherwise, the result will be totally awful. So that's something that we don't have. The other one is that the subdevices in the kernel are pretty much isolated from each other. At least when it comes to user space API. So I mentioned that a subdevice can have a video node and expose an API to user space. And so user space can configure formats on the different subdevices, can configure controls. But there's no way to do that in an atomic fashion. User space has to go through all the device nodes for every subdev and set the controls, one after the other. If you do that while video is streaming, there's no guarantee that they're all going to be applied on the same frame. So that's a problem we have. A third one is, well, I mentioned that you can set controls for every frame. There's no guarantee that it's going to be synchronized with the buffers, but you can do that today because controls can be modified in Video for Linux while the video stream is active. When it comes to format, however, well, there's no real restriction about not being able to set formats while the video stream is active. But in practice, it's very difficult to implement for drivers because they need to ensure that they have a coherent state of the whole pipeline when it comes to formats, and especially that the outputs of your pipeline going to the video, to the DMA engine, will always fit in the memory buffer because you don't want to overflow the buffers you have there. So formats are a bit difficult to handle, and the way it's done today, if you want to switch formats during the video stream, is that, well, you set the formats, you start your video stream, you capture one or a couple of frames, and you stop, reconfigure the formats, start, capture frame, stop, and repeat. When you have a memory-to-memory video processing engine that can do scaling, for instance, and blending with multiple video streams, you might want for every frame to change the format and reconfigure the pipeline. And so today it involves stopping the video stream and restarting it for every frame, which also involves dequeuing all the buffers and having to handle cache management every time you restart a video stream. And that's extremely expensive. That's pretty much unusable from a performance point of view in some of the use cases we have. So that's another problem. So now it's time to talk about the solutions, or at least proposed solutions. The request API is not upstream yet. That's a work in progress. We've been discussing that for at least the last 6 months, I believe, maybe more than that. Hans might be able to confirm. Yeah, but not much work in the beginning, but yeah. So I mentioned 3 different problems. We're trying to address them and possibly others as well. So that's not upstream. It's work in progress. The code is available. It's in a public Git tree. And there's active development on that, not as fast as I would like, but it's definitely not a project I want to give up on, and that's something that's really needed by, well, multiple vendors. So the way that works is that conceptually, at a high level, you group all your configuration parameters in what we call the request. So that can include formats, scaling, cropping. That can include controls. That can include buffers as well, when you want to queue a buffer and make sure that the controls are applied for the right video frame. And you group all that in a request object. And from a use space point of view, well, you set controls. There's a Video for Linux API for that. You queue one or multiple buffers, depending on how many video nodes you have. And then you issue an I/O control to queue the request. So all the parameters that have been set here, the buffer here, all that is stored in a request object in the kernel. And when user space calls the request queue command, that request will be queued for processing. And it will be, obviously, the responsibility of the driver to make sure it applies the parameters at the right time and in an atomic fashion. Depending on your hardware, that might be easy or more complex. Some hardware actually might not offer you any guarantee that's doable, so in that case, it might still be a best effort approach. But if your hardware allows atomic configuration, then you have a single entry point for the driver where it has all the needed pieces of information to configure the device. You can do that if you need to set formats as well. The initial approach is that we've been trying to reuse the existing Video for Linux API and the existing Video for Linux subdev API. So we're using the same I/O controls that are used today to configure the formats and set the controls. For some of them, we're able to extend them with additional parameters to tell the kernel this needs to be applied to a particular request. For some of them, we don't really have, because we don't have reserved fields anymore in the I/O control structures. For some of it, it's difficult to extend them. So we can't really pass that additional parameter. So the first approach that was proposed is to start by a new call, a new request command for the device. That's the begin command. So when user space issues a begin command, then the kernel will know that all the I/O controls that deal with formats and parameters will then apply to a particular request. So they don't have to be applied directly to the hardware, but they're going to be stored in the request that was started when you begin. And then when you're done setting all the parameters, queuing your buffers, then you queue the request that you opened here. So that's kind of way to have a transactional-based API on top of an existing API that doesn't support transactions. There's an additional problem to that. We discussed the media controller API a bit earlier, and I mentioned that it does two things: exposing the topology of the device to user space, and also offering user space a way to set up the links and activate, deactivate links so that it can change the pipeline routing at runtime. And that's something we need with the request API as well. So we have needs to be able to set the formats, to set the controls, to synchronize that with the buffers, but also to reconfigure the video pipeline dynamically. So we need to be able to set links and store that in the request as well. So if we go back to the previous slide, then you see that all this is done on video nodes or on subdev nodes. It doesn't involve the media controller API here. And that's a problem if you want to be able to set up the links. So next step in what has been proposed is to actually handle the requests not on the video for Linux device, but to extend the media controller API with the request processing. So instead of beginning a request on a video node, you go to the media device, that's the device that encompasses all your video nodes and all your sub-devices, and create the request there. So the API is slightly different, we'll come back to that later, but you basically allocate a request. Then you can set up the links, you can set the formats as before, set controls, queue buffers, and then queue the request the same way, except that you do it on the media controller device. So it's at a higher level on a device that actually has a view of the whole topology and all the pieces that are inside your hardware device. So that was the second step. When it comes to the implementation on the kernel side, well, all the request objects are reference counted. So when you allocate a request, yep?
So going back to the previous one, are you going to talk about error path if you make a request that the hardware doesn't support?
Yes. So I wasn't gonna mention that specifically, but the idea is that if a parameter is not supported, and that can be detected when you set the parameters here, well, then the IO control will return an error immediately, like it does today with the Video for Linux subdev API. If that cannot be detected because, for instance, the error comes from multiple parameters that are incompatible with each other, then it's going to be the queue call here that is responsible for validating the request. And if it finds out that the request is inconsistent and cannot be supported, then that one will return an error.
So those are all validation errors. What if the hardware fails to do something for some other reason? Do you register a callback?
So there's two cases. You mentioned that's validation indeed, and you should try in the driver to capture all the possible error cases at validation time, at least anything that you can foresee. And the idea is that once it's done, once you queue the request, once the request has been queued, it will be processed, assuming that the problem, the error, comes from the device and not from the driver, because if it comes from the driver, you should be able to catch it at validation time. But if it's the device that returns an error, then you can, well, there's multiple options. We don't have anything implemented for that at the moment, but we can definitely send an event. We have an event API in Video for Linux, so you could send an event to user space saying, oh, the request has failed. So that's one way to do it, and then you could, through the request command API, you could possibly query a state of the request to see what has failed. But from my experience, most of the errors can be caught during validation. If you have something that fails at runtime, that's more or less puts your device in a state where you have to stop everything and reset the device. So that can happen, but usually when it does happen, it's really a fatal error that can't really be recovered transparently, at least for the application. So requests are allocated and reference counted. So when you have a request object that you allocate, I mentioned that's done with the media controller API. So you have open your media controller device node. You have a file handle, that's the FH here. Because you've opened the device node, you issue an IO control to allocate the request. The request is allocated and an ID is given back to user space. And there's one reference from the file handle to the request. Request objects need to be global to the whole device. So we need a lifetime management policy there. And by reference counting them, we know that once a request is allocated, first of all, if user space closes the file handle, that gets rid of the last reference and the request will be deleted. So we know that there won't be a way for user space to allocate a request, close the device, and have an orphan request in the kernel, multiple ones that will just consume memory. Then when your request is queued, there's also a second reference from the request queue, meaning that at that point, because the request will be processed by the hardware at some point, if you close the file handle, you end up in this situation. You don't have two references but a single one, but the request object is still available. Then once the request has been queued, it has been processed by the device and complete, at least if you have closed your file handle, there's no reference anymore, and the request object is deleted. So that's pretty simple lifetime management, but that saves us from having to explicitly delete requests from user space. We can still do that. There's an API for that in case user space finds out that it has allocated requests but doesn't need them anymore, so doesn't need to queue them, and doesn't want to close the device node for cleanup. So it can explicitly delete them, but that will just remove one reference. So there's another reference within the kernel. The request object will be kept. The initial idea was to base, inside the kernel, the implementation of the request API on the video for Linux control framework. So the control framework is a library within the kernel that drivers can use to handle the video for Linux control API. So that's setting controls. Controls can be interdependent. The API to use space is pretty simple, but at least in the concept, but actually implementing it correctly can be quite complex. So we've decided to have a library in kernel space to handle that for the drivers. And we thought that the best way would be to base the implementation within the kernel on that library. That caused an issue in the sense that the control library, the control framework inside the kernel doesn't handle formats or scaling, cropping, and all that. So the initial idea was to model actually the formats as separate values that could be stored in controls within the kernel, not exposed to user space, but handled as controls within the kernel. So if you want to set your frame size resolution, that it's just a width and an eighth, that's 2 parameters. If you want to set a crop rectangle, a compose rectangle, it's 4 parameters. So that was the initial idea. But then, as I mentioned, we also need to store more information about the links, for instance. And that was getting quite complex to store in the control framework. So at least I decided to try a different approach and go for entity request data. So the idea is, instead of using the control framework, is to make it possible to store for every request custom data for each entity in the pipeline. So that means that if you can do that, for each request, you have a store where you can put data. And in the video for Linux case, when you have a subdev and a video device, then the implementation had two different kinds of data, a subdev-specific data structure and a video device-specific data structure that would store different parameters. And every time you would set a format or set a control, then the values would be stored in that object for the request. That's a bit limiting for what we want to do because, again, it doesn't store the link configuration. So we have per entity data, but we don't have data at the media controller level there. And also the data structures that we store for each entity depend on the type of the entity, but they cannot be extended by the drivers. So that's a limiting factor. So I'm going to address now the next steps that I'm working on. And I would also like to get feedback on possibly the current implementation, the current concepts, and the next ones to see if you might have use cases that are covered by what is going to be presented, in which case I would be really happy, or if few use cases would have a need for the request API, but not covered by that. So the first idea was to extend the per entity data that use a structure that was specific to the data type with the concept of an entity state and a media device state. So the idea of the state is that it doesn't set in stone the type of data that you want to store for a particular entity. And so the type of data is, the data can actually be extended by the drivers, and drivers can store all kind of custom information that they need. And that's quite similar in concept to the DRM KMS atomic update API, where the kernel models the state of the whole device through state of different pieces that can be extended by each driver. And so the way that is handled is that we have 3 operations for the state. You have a way to allocate a state. You allocate a piece of memory and initialize that with either default values, or if your driver wants to be a bit more clever and want to be able to recover from configuration that is passed by the bootloader. It's a bit more important for display, a bit less on the video for Linux side, but there are definitely use cases for that. You might want to read back the initial state of the hardware device to create the software state that corresponds to that. So that's the first operation, allocating a state. The second one is duplicating a state. As I mentioned, the state can be extended by the drivers, so the core code cannot just duplicate a state object because it doesn't know what's stored in there. There's core information that needs to be stored in the state because the core code will need that, but all extra information is specific to the drivers, so drivers will need to implement a state duplication API. And the third one is deleting a state for the same reason, because the state object is something that driver specific. Freeing it and possibly cleaning the content of the state is something that, that is specific to a driver. It needs to be implemented by the driver. So the way this works, well, I'll stay on this slide for now. The way this works is that when you create a request, the kernel will start by duplicating the current state of the device. So the current state of the device is a software state that models the state of the hardware. And so the kernel will duplicate that and then modify parameters based on what you want to set. So if you set controls, if you set formats, it will store that in the state. So it will modify that duplicated state. And then finally, when you queue the request, the new state will, at some point while the request will be processed, become the active state and will be applied to the hardware. So that's really the key concept behind that. One really interesting side effect is that we have lots of drivers today in Video for Linux that do store hardware state or device state in driver-specific data structures. And there's lots of those fields there that are actually pretty much the same for all drivers, storing the active resolution of your video stream, storing control values. All that is stored in driver-specific structures, but that's just duplicating code. So if we can have a concept of a central state, standard state object that can be extended by drivers, then all the standard information can be stored there, and that can simplify the driver implementation. So it's a good side effect of the work. It's not the main goal, but it's a good side effect. But it also means that when you queue requests, we need to be able to handle a sequence of requests. So you prepare a request, you set parameters, you queue that for processing, and you can prepare the next or 2 or 3 or 4 extra requests on top of that and queue them as well. As I mentioned, when you create a request, we start by duplicating the active state of the device. If we just do that, duplicating the active state of the device, if there's a request that has been queued but not applied yet, you're going to duplicate a state that's current. You're going to modify that state and queue that one. But once a previous request is applied, you will have a mismatch between the state you have that you will need to apply next and the state of the hardware. So to solve that, the idea is that when you create a request, instead of duplicating the current state, we need to duplicate the state corresponds to the last request that has been queued, or the request that will be queued just before that. So it's going to be, at least with the current implementation and current idea, the idea is to make it use space responsibility. When use space wants to manage multiple requests and have them in fly, it's going to be use space responsibility, application responsibility to start when creating a request to tell the kernel which state to base it on, so which request to base it on. So the sequence of requests needs to be handled when allocating a request for that reason. And also when the request is queued to the driver, then the driver will make sure that it's queued in the same order as the allocation order. Otherwise, it's user space messing it up. If user space tells that it wants a new request that's based on number 3 and queues it after number 4, after number 2, then there's an issue in user space, and that will be rejected by the kernel. That's a bit more complex than what we do in, again, the DRM and KMS subsystem and API, because there's a single I/O control that can be used to create what's equivalent to request, to set all the parameters and queue in a single go. And if you can do that, then by definition, that becomes atomic. And the order of the requests is the same as the order in which they're allocated and filled with data and queued. So that's one possible improvement of modification, is instead of setting up a request on multiple video nodes, setting up parameters on multiple video nodes, we might actually want to do that in a single go, in a single IOCTL. That would need to be on the media controller device, and we would pass, well, basically a list, an array of all the parameters that need to be put in the request. If we do that, we solve the queuing sequence problem. The issue there is that you get rid of the whole V4Linux and V4Linux subdevice API, and you replace that with a single I/O control to create, fill, and queue a request. So I don't know if that's the best idea, because that requires pretty big changes in user space. But user space using the request API will need to be modified anyway, because there's new I/O controls, new concepts that need to be handled. So that's an open question. Another item that we need to implement is to actually go the other way around, is to be able to pass metadata back from the kernel to user space. So everything I've talked about until now is about configuring the device. But you might also want to get information back from the device for every frame you capture. An example of that is, again, I mentioned camera with the camera sensor and exposure bracketing. You want to be able to set the exposure time for every frame, but you also want to know what exact exposure time has been used to capture a frame, whether the frame has been exposed by the flash, by the camera flash, and all possible parameters. So if you have hardware that can give you the parameters back, we need a way to pass that back to user space, and we don't have a way to do that in V4Linux today. And using the request API, once you queue a request with capture parameters, the request is being processed. Once that's done and metadata about the frame is available to the kernel could store that data inside the request and then notify user space. And user space could then take the request object back and read the information. So read controls, read formats possibly, although formats are probably something that will not be changed automatically or autonomously by the device. And that's another use of the request API. So it's being able to read back metadata from kernel space. Before we go to questions and answers, there's RFC patch series that was posted. The link is there. There's a public, as I mentioned, Git tree for development. So wait until people are done taking pictures before going to the next slide. But that's available in the slides I've posted, and if they're not available on the conference website, they should be soon. So you can get them there. Then if you need to interact with us, with the V4Linux and media community, we have a mailing list. You can always use my email address as well, but it's much better to send a request to the mailing list and just CC me. So with that being said, questions and hopefully answers.
Quick clarification. You
Yes.
said, like 3 practice, the APIs are still there. You can still do them on your own, correct?
Yes. So the request API will not be mandatory. That's the first thing. You will not have to create requests. You can still use your video for Linux device the way you do it today. If you're not interested in the features that are provided by the request API, and many applications will not be, if you have, I don't know, webcam application on a computer, there's absolutely no use for that. Then the whole video for Linux API is exactly the same. It doesn't change. Implementing the request API through multiple video nodes, there's going to be extensions to the current API, a couple of new IOCTLs, possibly new fields in current IOCTLs as well. If we do it this way, through a single IOCTL, that replaces the current video for Linux API, but again, it will stay for all the existing devices, all the existing applications, and all the new ones that don't need requests. So internally, the idea is that internally, that single IOCTL with a single buffer that contains all the parameters will be parsed by the kernel, will be split in states for all the media entities, and will be passed to the drivers in exactly the same way as would be done by a driver that doesn't use the request API. So for most drivers, it should be transparent. We don't want to have two different APIs in kernel space. Obviously, kernel space APIs between sub-devices need to be extended, so there will be a transition during which, well, new drivers are supposed to use that, and all drivers, if they need to use the request API, will be transitioned. We have quite a lot of subnet drivers, so it's not really feasible to modify all of them at the same time. But yes, the current APIs will stay. Yes?
Yes. Question. So on the last slide, when you're talking about the getting the metadata, do you have a kind of a schedule or an ETA for when those work will start?
Not really. I'd like to do that as soon as possible, but as I mentioned, it's work in progress. I expect lots of discussions to be needed because, well, I know that lots of people are interested. They will review the patches, and I expect that we'll need quite a few rounds. So I wouldn't be surprised if we have 10 or 15 rounds of patches. And because this is not the only project I'm working on, depending on my availability, so I would certainly welcome contributions. If someone wants to help me with that, we can discuss it and discuss the directions, but I don't have an ETA at the moment.
That type of issue actually is quite often in the AI community. So just the synchronization between the cameras and the IOU, that
Yes.
solves a lot of issues.
Yes. Yeah, there's a couple of projects where that could be useful. So I know it's a much requested feature, but unfortunately, I don't have an ETA for that. I'll do my best. I'll take one last question because I see that we don't know, and then we can have questions in the hallway. Yes?
So when you allocate the request handle and you're passing that back to
Maybe that?
you allocate the request handle, and then you are trying to build up the state of the request and passing that handle into the
Yeah, so when you look at the request, the kernel will give you a handle, so that's just a number. And the idea is to pass it explicitly through the IOCTLs, the existing video for Linux IOCTLs, at least the ones that can be extended. As I mentioned earlier, there were a couple of issues with that, with IOCTLs that cannot really be extended easily. That's why we had this begin call. But that's the part I want to get rid of. So the ICTLs that can be extended with the request ID, I want to do that. The other ones, maybe I'll create a new version, or possibly still extend in some way. The details need to be discussed, but I want to pass the request ID explicitly. And if we go for this implementation, then obviously there's no need for that. Okay. Okay, so if there's more question, let's go to the hallway for that, and I'll let the next speaker have the room. Thank you very much.